Hello, welcome to the Let's Go Library series of Bytes of CSE, where I discuss important features of various libraries used in data science, artificial intelligence, and today I'll be doing NumPy. Oh, by the way, this episode is optimized for listening experience. So if you're watching the video version of it, you can easily switch to the audio version with a YouTube Music app. Now let's dive in. NumPy is a fundamental package for scientific computing in Python. This is a Python library that provides a multi-dimensional array object, various derived objects like masked arrays and matrices, and an assortment of routines for fast operation on arrays. NumPy provides an n-dimensional array type, the ND array, which describes a collection of items of same type. All ND arrays are homogeneous. Every item takes up the same size block of memory and all blocks are interpreted in exactly same way. When you create a NumPy array, you will typically pass on an n-dimensional list of values and optionally the data type of the values passed like float, double, etc. In addition to the basic types like integers, float, the data objects can also represent data structures. An ND array is usually a fixed size multidimensional container of items of same type and size. The number of dimensions and items in an array is defined by its shape. Shape is represented as a tuple that contains number to represent sizes of each dimension. Now, a valid question you will be asking me is Python already supports array, so why do we need a separate NumPy array? This is because NumPy arrays favors advanced mathematical and other types of operations on large number of data. Typically, such operations are executed more efficiently and with less code than is possible using Python's built-in sequences. Suppose you have two 1D arrays and you want to do an element-wise multiplication of each element of the arrays and store that in another vector or a 1D array. Traditionally, in Python, you will have to iterate element by element, multiply, and keep appending to the new array that holds the result. If the array contains millions of elements, imagine how inefficient that would be. But in NumPy, you simply write like C equals to A into B because element by element operations are the default mode when an ND array is involved. What makes NumPy super fast is vectorization. There is no need for any explicit looping, indexing to be set up by the programmer. In the code, these are done just behind the scenes. Vectorized code is more concise and easier to read. And fewer lines of code also means fewer bugs. The implicit element by element operation is called broadcasting. In fact, all operations in NumPy, not just arithmetic operations but logical, bitwise, functional, all of them behave in this implicit element by element fashion, that is a broadcast. The arrays can be of different shapes and you can still carry out the operation, but of course there are restrictions for this. The rule is like when NumPy carries out operations between two arrays, it will always compare their shape from right to left. Two dimensions are compatible if they are of same shape or one of them is 1. Also, if the leftmost dimension is missing in one of the arrays, that is considered to be 1 and the array operation is carried out. Let us take some examples here to better understand the topic. Suppose there are two arrays of shapes 3, 4, 5 and 4, 5. The rightmost dimension of both arrays has shape 5, which is compatible. Then the next dimension is 4 in both. Again compatible, and the leftmost dimension of one array is 3 and this dimension is missing in the other one. So the missing dimension will be considered as 1 and the array operation is carried out. Let us consider another example, like suppose two arrays are of shape 3, 4 and 3, 1. So the rightmost dimension of one array is 4 and the other one is 1. According to the rules of the non-leftmost dimension, either dimensions must match, one of them has to be 1. So in this case, one of them is 1, therefore compatible. And the leftmost dimension of both are 3. Therefore, the array operation is valid. And for our last example, let the array dimensions be 3, 4 and 3. I will pause and give you a moment here to figure out the compatibility. Yes, that's right. The operation is not valid. Since the rightmost dimension of one array is 4 and the other one is 3, that breaks the rule. The arrays could have been compatible if the shapes were 3, 4 and 3, 1. As I said earlier, instead of requiring explicit element-wise looping in Python code that makes the process time-consuming, it automatically aligns and expands a smaller array to match the shape of the larger array. Then low-level C code is used to enable vectorization. C is a compiled language that translates directly into machine code. This allows the CPU to execute instructions without an intermediary interpreter. NumPy performs iterations in C since it offers the advantages of static typing, where data types are fixed and known in compile time to make sure that the mathematical operation is valid for this array. Also, C stores elements in contiguous memory blocks that allows the CPU to fetch large chunks of data into high-speed cache at once, and C compilers can use SIMD instructions, that is single instruction multiple data, to allow a single CPU cycle to process multiple data points, like adding 8 numbers at a time. Now let us get into NumPy basics. Convert any Python array to NumPy array by passing the array as an argument into the function np.array. It preserves the shape and size of the array, only the array type is changed to NumPy. Now you can set your desired data type or dtype as is called in NumPy while creating the array. But this is totally optional as NumPy infers the data type if not mentioned and also apply promotion rules where necessary. As with other container objects in Python, the contents of an ND array can be accessed and modified by indexing or slicing the array and via the methods and attributes of the ND array. You can even mention the data type of your NumPy as per the precision you are looking for. For example, your Python list contains both float and int. When you pass on that array into np.array function, set the type to say np.double, based on which sets the precision accordingly. Now, what if you pass a Python list with integers, float and string? Well, NumPy implicitly sets the data type to Unicode string with maximum 32 characters depicted with a greater than sign and U32. So yeah, you do not really get any syntax error if you pass such an array. By the way, there are 5 basic numerical types supported here representing booleans, integers, unsigned integers, floating point and complex. Those with numbers in their name indicate the bit size of the type. That is how many bits are needed to represent a single value in memory. Easily cast an array to a different data type in NumPy by using asType, like myArrayVariable.asType within bracket float that converts the array variable myArray to float. Now this is a preferred way to convert. Alternatively, np.float bracket myArrayVariable will also work. Different ND arrays can share the same data, so that changes made in one ND array can be visible in the other. That is, an ND array can be a view to another ND array and the data it is referring to is taken care of by the base ND array. ND arrays can also be views to memory owned by Python strings or objects implementing the buffer or array interfaces. So if you're curious to know that if arrays, like 2 arrays share memory, you can use numpy.shares memory and within bracket you can just pass on the variables. This quickly finds out that if one array is referring to the other. All the basic Python slicing and indexing are supported here, and error is thrown if you try to access an index out of range. There are some fancy indexing techniques supported in NumPy which I will discuss a little later. But first, I would like to tell you how to create a NumPy array. I've already discussed and showed you if you're watching the video and the basic NumPy.array method of creating a NumPy array. Alternatively, you can create a new array using numpy.ndArray and pass on the shape of the array as a tuple. By default, the data type for that array is set to float and the array is initialized with some garbage values. in practice, the two most common ways you will be using to create a NumPy array is using numpy.random.rand, where you will be passing the shape of the array and it will create an array of the specified shape and fill it with random numbers from a uniform distribution between 0 and 1. The other one is numpy.random.randn, where the samples are returned from the standard normal distribution. There are several NumPy methods that initialize the values with garbage or 0 or 1 and so on. Now let's quickly go through those. You have np or numpy.empty for initializing an array of given shape and size and d-type. Even though it is supposed to be an empty array, I have seen that the uninitialized array contain garbage values. Next we have np.empty-like, where you pass another reference array and ask the NumPy to return a new array with the same shape and type. Like this, you have numpy.once that initializes the array of your given shape and size with values 1, numpy.once like, and similarly we have numpy.zeros and numpy.zeros like that sets the value to 0. Empty, unlike zeros, do not set the array values to 0 and may therefore be marginally faster to create. On the other hand, it requires you to manually set all the values in the array and therefore use it with caution, because as I said before, it actually initializes with some garbage values. Easiest way to set the value, however, is to use the function fill on this empty array, where you will be passing on any scalar value and every element in the array gets set to that value. So if you are using this scheme, like this fill value scheme, make sure that you would like to set the value of your array to anything other than 0 and 1, because NumPy already provides numpy.zeros and numpy.ones. And then you have numpy.I, where a 2D array is returned of a particular shape specified with zeros on diagonals and ones everywhere else. Similarly, an identity matrix is returned of a specified shape with ones in diagonals and zeros everywhere else using np.identity. Example, np.identity5 returns a 5 cross 5 identity matrix. Initialize an array of any shape with a particular value using np.full and passing the shape and fill value as arguments. And yes, full also has its counterpart, full like. Often in artificial learning, you might have to manipulate the data by adding some cushion values or additional noise. So NumPy provides several ways to create vectors or one-dimensional ND array with values that adhere to your preferred range. A very common one is np.arange, which is similar to the Python range function. This takes a start value, a stop value, and an optional step size, which by default is 1. You could also set the type of the output array using the dtype parameter. If you opt that out, the data type is inferred from the other input arguments. The values generated includes the start value but not the end value. This method is preferred for integer step size. If you intend to use fractions as your step size, say 0.1 or 0.5, use np.linspace. This returns evenly spaced numbers over a specified interval. Like arange, you will need to enter the start value, stop values, both of which, by the way, is included for generating the numbers by default. And of course, you can opt out of including the stop number by setting the endpoint to false. Then you can optionally set the number of values to be returned in this range. If you do not specify the number of values parameter, 50 values are returned by default. You could also generate numbers evenly spaced on a log scale, where the start and the end points are basically logarithm of a base, which you can specify, and otherwise if you don't specify, it will be 10. So if you want to create an ND array using numpy.logspace within bracket 2, 3, and if you set the number of samples to 5, you will get an ND array with 5 values between 100 and 1000. Logspace in fact lets you create even two-dimensional arrays by entering the start, end and base values as same shapes arrays, and you could choose to arrange as rows or columns. If you are listening to the audio and if this part is not clear, you can switch to the video and see the code illustration of it. You also have geom space, which is similar to log space but with endpoint specified directly. Each output sample is a constant multiple of the previous. You can generate samples from a uniform distribution using numpy.random.uniform, and you can pass the lower boundary, the higher boundary, and the size. If you like to create an array that contains value from Gaussian or the normal distribution, use numpy.random.normal, where you will be mentioning the mean, standard deviation, and the intended size of the array. Now this one is very useful to add noise to your data, which we prefer to sample from a normal distribution using mean 0 and standard deviation of 1. There are some more features like mesh grid, O-grid, which are not quite used as much in real world. You could go through the NumPy documentation for it. It is not something you must know. Like, it's not a must know thing, but it's kind of good to know concepts, and I'm not explaining these here. Coming back to the fancy indexing, which I said earlier, I will discuss two advanced indexing techniques here. First one is np.take, which accepts an array and the indices to output the values contained in those. But what is so fancy about it? Well, you can pass on the indices as list arranged in any dimension, and the output will mimic that dimension. Say your array is 1D and you want to show some of the elements in 2D. Simply arrange the indices in a 2D layout and you get the output of the same shape. Next is np.put, where you can pass on the array, indices, and values as list. The original values of those indices will be replaced with the values specified in the same order. And be careful here, because this actually changes the values of your original array. Be careful. Now let us move on to the main part of the episode, that is what to do with a NumPy array. There are some widely used basic functions used by every NumPy users, like shape to find the shape of the array, dtype to know the data type of the elements contained in it, then ndim to find out the dimension of the array, size to find out the number of elements held by the NumPy array, and dot t in caps to transpose an array. We have already seen a number of ways to create an array in NumPy. There are some additional methods like np.tile that constructs an array by repeating the number of times given by the repetitions. The repetition argument can either be a number or a tuple. Each number in the tuple represents how many times the array contents are to be replicated along each axis. You can in fact pass on a 1D array and cast it to a desired dimension with a desired number of repetitions. If you like to repeat each element in the array, you can use numpy.repeat. This is simple, but you cannot upgrade the dimensions of the original array like you have done using tile. Dimension manipulation is very important in machine learning and is often used to make the arrays to be of compatible shapes for matrix multiplication. Let us go through some of the dimension manipulation and reshaping functions in NumPy. There are two ways to resize the array. First is by using np.resize, where you can pass on the array and the new dimension as argument. As you specify a resize dimension greater than the size of the array, then the new array is filled with repeated copies of the original array. The second way to resize the array is to use array variable name .resize. If in this case the resize dimension is bigger than the original array, the extra values are filled with zeros. In this second method of resizing, if the original array has been referenced, then by default you cannot resize it. You also need to set the ref check parameter to false in order to do that. So these are small details which are worth knowing, because resize and reshape are used a lot for array manipulations. Having said that, let's talk about reshape, which is another very powerful and important array manipulation tool. Here the data can be reshaped, but if the size of the reshaped dimension is bigger than the size of the original array, it will throw an error, which makes it different and in fact more useful than resize in cases like size conforming in matrix multiplication. You can add a new dimension to an array using np.newAxis. You can broadcast an array to a new compatible shape using NumPy.broadcast2 function that returns a read-only view of the original data with the specified shape. Suppose you have a 1D array with elements 2, 3, 4. If we broadcast this shape, this array to the shape 3, 3, like the elements 2, 3, 4 is repeated to create a 3 cross 3 array without actually copying the data in memory. So this makes it a very memory efficient operation. When you're dealing with image data, it is very important here to flatten that, because Panda series, then scikit-learn, they expect data to be in one dimension. So let us see what is on the table regarding data flattening in NumPy. There are two ways to flatten your data. One by flatten and another by ravel. The main difference between the two is flatten creates a copy of the original array and returns that, whereas ravel does not create a new array. Therefore, if you make changes to a ravel version of the array, those changes will be reflected in the original array. Flatten, on the other hand, since it creates a new array, all the changes are made to the copy, leaving the original version intact. Ravel definitely is more memory efficient and is faster. This becomes perceptible especially if you have to deal with very large data sets. Ravel is clearly the choice here. And flatten is mostly used when data safety and integrity is your concern. You can carry out operations, iterations in a copy while the original data stays safe. So choose ravel or flatten according to your use case. Want to move contents of an array access to another one? Use moveAxis. Pass on the multi-dimensional array, specify the access number where you would like to shift and the desired dimension where you would like to shift to. Sorry, I think I just made a mistake. If you want to use moveAxis, so you will first pass the multi-dimensional array. You will specify the access number which you would like to shift and the desired dimension where you would like to shift that data. You can also transpose the contents of a NumPy array in any direction using np.transpose. You can even interchange two specific axes of an array and return the view of the array with the dimensions reordered. This is a simple and efficient way to reorient multidimensional data without copying the underlying data. If you're wondering why on earth should I swap axes? Well, this is used mostly for data reordering. For example, deep learning frameworks like PyTorch and TensorFlow expect image data in format like batch, channels, height, width, while MATLAB uses a format like height, width, channel. Swap axis is helpful for reformatting the same data based on the kind of library used. Plus, data orientation is also helpful if you are dealing with recurrent neural network. Your data is often organized as feature time steps, while the RNN expects it to be time steps features. Hope you have noted the difference between move axis and swap axis. Let me know the difference in the comment section. Now, often for mathematical compatibility, we need to expand and again reduce the dimension. For that, use squeeze for reducing the dimension. Suppose you would like to glue two NumPy arrays together. There are three ways to do it: H-stack, V-stack, and stack. And yes, you have guessed it right. H of H-stack stands for horizontal, which stacks the array column-wise, that is side by side. In order to use H-stack, all arrays must have the same number of rows. It concatenates along the second axis for arrays of more than 2 dimensions. V-stack stacks the array on top of each other, that is, along the first axis. Therefore, the arrays need to have the same number of, yes, columns. Stack joins a sequence of arrays using a brand new axis. You can vertically or horizontally concatenate by specifying the axis parameter. In order to use stack, the arrays must have the exact same shape. Note that. Next, I'm going to talk about two extremely important predefined functions in array manipulation using NumPy, argmax and argmin, that returns the indices of the maximum and minimum element of a NumPy ND array respectively. These two functions are extremely important with respect to data science and machine learning. Suppose you're training a model to do a classification task. In this case, the output is generally a vector where each index represents a class. The model predicts a probability vector where each index contains a certain probability value. Using argmax on that output vector, you can find the index that has the highest probability value, which in turn gives you the class to which the image belongs. Because remember, each index here stands for a certain class and we are interested to label the content of the image rather than the raw probability. Like if you get a result like the image looks like 70% like a dog and 30% like a cat, well, it's not very useful, right? Similarly to these two is argsort, where the indices that sort the array is returned. By the way, you can sort an array plainly using simple np.sort, where you will be passing on the array and the axis you would like to sort the values. In fact, you can partially sort an array using np.partition to get the k topmost elements. It creates a copy of the array with the elements rearranged in such a way that the value of the element in kth position is in the position the value would be in the sorted array. In the partitioned array, all elements before the kth elements are less than or equal to that element, and all the elements after the kth elements are greater than or equal to that element. So that's why it's a partial sorting. Another very important vectorized tool in NumPy library is where, precisely numpy.where. This acts as a fast element-wise if-else statement, which is significantly more efficient than using explicit Python loops, especially for large datasets. The three mandatory arguments that the function accepts for this are number 1, condition, number 2, operation if the condition is met, and number 3, the else part. For example, if you have two arrays x and y and you would like to return x plus y if the value of x is even, else x minus y, then you can simply write it as np.where condition, that is x modulus 2 equals to 0, comma x plus y, comma x minus y. This is a very powerful function, and of course you can use it innovatively, say for pre-processing missing data or outlier data, and I of course leave that imagination and innovation to you. There is another use of numpy.where. You can get the indices of the array where value is confirmed to some condition. Say for example np.where within bracket array.variable greater than 100. All the indices that contains a value greater than 100 in the array variable are returned as a list by numpy.where in this case. So this is also a very important function used by NumPy users. Now coming to outliers, NumPy provides a simple way to deal with that using a clip function where you pass on the array the minimum and the maximum values the array can have. All the values lesser or larger than the specified mean and max are adjusted accordingly. NumPy, as many of you would be knowing, is used for data pre-processing, and when I'm talking about data pre-processing, how can I not talk about missing data? If you have np.nan type data in your dataset, you can confidently find mean, standard deviation, sum of any data column by specifying that column contains or might contain nan value, that is not a number value. How? By using np.nanmean or np.nanstd or np.nansum. In order to find out if a certain variable is a nan or contains a nan, simply use np.isnan. In fact, apart from just nan, you can amplify your data probing game using logical evaluation functions numpy.all and numpy.any, which are often used for data validation, conditional logic, mask manipulation, and so on. NumPy.all evaluates to true if all the elements of an array or a dimension of an array, like if your array is multidimensional, if you like to check the data for a specific dimension. So if all the elements evaluates to true, it will return true, else it will return false. By true means if the numbers contained in an array cells have a non-zero value, they are considered to be true. And yes, it includes negative numbers, and if there is a zero value, it is considered as false. So if any array content is 0, np.all returns a false. For np.any, if there is any non-zero value present in your array, it will return to true. So if your array has contained say 0, 0, minus 1, np.all will return false and np.any will return true. Often this is used along with other functions, important functions like isNaN, isFinite, isInfinite, isNegative infinity, isPositive infinity, isNot_a_time, like isNat, along axis. Like say you have a NumPy array and you want to check if any of the values is a NaN type, that is not a number type. If you pass on the array to np.isNaN and then add the logical any, like say if you have an array myArray and you would like to check if any of the value is if any of the value is a NaN type, you will just pass on like np.isNaN, within bracket you pass on the array variable myArray here dot any. If it contains any NaN value, the output will evaluate to true. If you use a plain isNaN, an entire array containing element-wise true or false value will be returned, and this becomes very tedious for large arrays. If you use this all or any, you get the initial information about your data. Also, you have support for isReal, isComplex, isScalar, and there are logical AND, OR, NOT, and XOR represented as np.logical_OR, np.logical_XOR, and so on. An important use case here is to check if a particular dimension of a NumPy array contains value in a certain range. Say if the values are greater than 10 and less than 100. So you will use logical AND here. You can even use all or any here for a concise information, which is again very useful. If you want to check if all the values in this in your NumPy array, say x is greater than 1, then just within third bracket write x greater than 1 and then use dot all over it. If all the values are true, it will return true, and if any value is less than 1, it will return false. I would request you to go through the NumPy documentation here and also try out on your own how to use these. And by the way, again, if you are confused, please switch on to the video version. The code will be showing how exactly this works. By the way, if you are wondering how to remember so many functions, especially the syntax, arguments for so many of them, fear not, because every object contains reference to a string which is known as docstring. In most cases, this docstring contains a quick and concise summary of the element and how to use it. Python has a built-in help function which can help you access this information. This means that nearly any time you need more information, you can just use help to quickly find the information you need. Say help within bracket np.isNaN, and you will get the full details and examples for that function. So just remember the syntax of help and names of the function you would want help with, and it will sort everything. And honestly, I find it far helpful than asking Google or any other chatbot. Having said that, let us learn some more functions that every data scientist or machine learning scientist will use at least once in their lifetime. Like there's an interesting function. Suppose you would like to insert a vector in your array which is already sorted and you do not wish to disturb that order. If you use search sorted function on that array and pass on the vector, it will find indices where elements of V can be inserted without disturbing the order. Now how cool is that? Sometimes it is also helpful to find out indices of an array that contains non-zero elements. So for that, use the non-zero function. You can reverse an array using flip, and if the array contains more than one dimension or axis as is referred here, you can optionally reverse a particular axis by passing the axis number as argument. For example, if you have a matrix or a 2D array, simply reverse only the rows by mentioning axis equals to 0. That is np.flip array variable, axis equals to 0. Now let us move on to a very important part in NumPy, which is the mathematical functions. In fact, it is the ease of implementing mathematical formulae that work on arrays is one of the things that make NumPy so widely used in scientific Python community. For example, let us consider the mean squared error formula, which is a central formula used in supervised machine learning models that deal with regression. Suppose you have two 1D arrays of n elements representing the predicted and the true values. MSE would be 1 by n sum over n predicted values minus true values, the whole squared. This can simply be implemented as error equals to 1 by n into np.sum within bracket np.square within bracket predictions minus labels. Here first subtractions happen, then they are squared, finally NumPy sums a value and divide it by n. Now there is a plethora of mathematical functions that are supported by NumPy that includes basics to trigonometric, to exponential, logarithmic, hyperbolic, floating point, rounding, statistics, linear algebra, and so many more. Like there are at least 60 of them. Then you have support for very important functions on matrix like matmul that does matrix multiplication over two matrices or 2D arrays fundamental to many mathematical operations in data science between matrix and vector, and this is also used in physical simulations and machine learning, particularly when calculating linear combinations or applying transformation to data points. Matmul can also be used for vector matrix product. In fact, it automatically adjusts the 1D array shape to 1 cross n or n cross 1 to facilitate the multiplication. If you are using higher dimensional array for matmul, the last two dimensions are treated as matrix and calculations are carried out in a stacked or batched manner. In neural network, this matrix multiplication is a core operation for forward and backward propagation. Weights are represented as matrices, input features are transformed into vectors or matrices, and np.matmul is essential for applying these transformations efficiently. You also have separate functions for dot product of two arrays, for two or more arrays in a single function call while automatically selecting the fastest evaluation order. Then dot product of two vectors, outer product of two vectors, tensor dot product along specified axis, raising a square matrix to the integer power n, and you can find detailed information about these from NumPy official documentation on linear algebra functions. Naturally, neither me nor you can learn and memorize all of them in this episode. So what I've done is I have jotted down the most important ones to start with, and those will cover at least 95% of your programming needs for data science and ML, even on the research level, I would dare say. I have compiled those list of functions along with the link of each function to the original NumPy documentation in a PDF and have added that to the description box. Do download that if you want to keep those must-know functions handy. In fact, NumPy also offers set operations like union, difference, intersect, etc. and Fourier transform functions heavily used in signal processing. You will find important functions to know for those two in the PDF. All of these functions are like one-liners and they greatly help with cutting down your code footprint. All you have to do is study the equation you want to apply, then use these predefined functions in the correct order or sequence to get the result. In fact, you can also carry out integration along a given axis using composite trapezoidal rule. If your data contains np.nan values, you can use same mathematical functions by specifying nan before them, like nan prod or nan sum for product and multiplication. This way the function will simply ignore those rules and return the result, and hence you will not encounter any error while carrying out those mathematical functions. I have not included the last two, that is the integration and the nan thing in the list, and this is actually for two reasons. Number one, probably you will never use integration, and secondly, real world data does not even contain np.nan value. Those are far messier than you can imagine, and you will need to clean the data first, and then you can choose to fill those unavailable values in any way you would like to do that. But it is good to inform you about the nan supported mathematical function just in case you would like to convert those unavailable data points as np.nan. Then there is a functional programming where you would define a function and then tell NumPy to apply that function to 1D slices along a given axis or repeatedly over multiple axes, specifying like np.apply along axis for single axis and np.apply over axes for multiple axes. You will pass on the name of the function and axis as argument in case of apply over axes. You can define a vectorized function which can take a nested sequence of objects or NumPy arrays and inputs and return a single NumPy array or a tuple of NumPy arrays. To elaborate a bit more, suppose you have a normal Python function, say myPyfunc, that takes two variables a and b. So if the value of a is greater than b, the value a minus b whole squared is returned. Otherwise, say a plus b whole squared is returned. Now you define a variable, say npfunc, and initiate that to np.vectorize, and then you pass this myPyfunc. Now you can pass on an array for a variable a and b into that npfunc, and the function uses vectorization to produce a result. If this part is confusing you, pause the audio, switch over to the video version, rewind, and go through the part again to find out that how is it actually happening programmatically. It's displayed there. You can compare two array using array equal. If you are interested to know that if values exactly match, and if you like to check both, if the values and the shape, like exactly if they match, you need to use array equivalent. Then some other functions are there like greater, greater equal, less, less equal, equal, not equal, that can be carried out element wise on two NumPy arrays to check the values. You can even have options to load and save NumPy objects. You will at some point of time want to save your arrays to disk and load them back without having to rerun the code. Fortunately, there are several ways to save and load objects with NumPy. The NT array objects can be saved to and loaded from the disk files with load.txt and save.txt functions that handle normal text files. Load and save functions that handle NumPy binary files with a .npy file extension and a savez function that saves NumPy files with a .npz file extension. The .npy and .npz stores data, shape, dtype, and other information required to reconstruct the ND array in a way that allows the array to be correctly retrieved even when the file is on another machine with different architecture. So, if you want to store a single ND array object, store this as a .npy file using np.save. If you want to store more than one ND array object in a single file, save it as .npz file using np.savez or savez, whatever you like to call it. You can save several arrays into a single file in compressed NPZ format with savez_compressed. So there are also different ways to actually save text files like CSV or .txt files. What I felt was I would in this case recommend you to actually go through the NumPy documentation if you would like to use it, because truth to be told, we generally do not use much of the NumPy save load functions, because libraries like pandas and pytorch, they already have save and load options, and these are used more, at least what I've seen in my case and in the case of my peers. So this is again to inform you that yes, you can save those NumPy arrays if you would like to in your system, and later on load that. Now let us discuss about masked array, which is another very useful tool in NumPy library. In many circumstances, datasets can be incomplete or tainted by the presence of invalid data. For example, a sensor may have failed to record a data or have recorded an invalid value. The NumPy.ma module provides a convenient way to address this issue by introducing masked arrays. A masked array is a combination of a standard NumPy.nd array and a mask. A mask is either a no mask, which indicates that there is no value, no value of the associated array is invalid, or an array of booleans which determines for each element of the associated array whether the value is valid or not. When an element of the mask is false, the corresponding element of the associated array is valid and it is said to be unmasked. When the element of the mask is true, the corresponding element of the associated array is said to be masked, which is invalid. The package ensures that the masked entries are not used in computations. For working in your dataset, use the set the mask condition, like say masked condition equals to data equals to -9999 or data equals to np.nan, where data is the name of your NumPy data array. Apply this to your data using the masked where method of the NumPy.ma module, as say masked data equals to ma.masked where mask condition comma data. This mask condition and data is passed as an argument, and now you will get your masked array where you can safely carry out your desired operation, and NumPy will simply ignore the invalid data entries. Specifically put, you can apply mathematical functions directly to these masked arrays, which will automatically skip over any masked values, making it easier to compute statistics such as mean, median, standard deviation without the need for complex logic to handle missing data or those invalid data. The streamlining of the data operation enhances productivity and reduces the risk of errors in data analysis. Now again, for this part, if you are getting confused, if you're listening to the audio and getting confused, please switch over to the video version. I have shown the code there. That will be easier for you to follow. Now we progress to the last two segments of the discussion. The first one is time delta and date time in NumPy. Now this part can be definitely skipped if you like to, because there is this time delta and NumPy data type is supported. There is time delta and date time data type supported natively by array data types in NumPy. Time delta here are referred to as datetime 64 and time delta 64, since there is already datetime and time delta in Python. Like Python, date class dates are expressed in the current Gregorian calendar, indefinitely extended to both future and in the past. But there is also a difference here. Python date supports only years in the range 180 to 999980, but datetime 64 also allows for dates before Christ era. Years before Christ era follow the astronomical year numbering convention. That is, year 2 BC is numbered as -1, year 1 BC is numbered as 0, and year 1 AD is numbered as 1. Time instants are represented counting hours, minutes, seconds, and fractions from midnight. Each calendar day has exactly 86,400 seconds. The date units available here are year as Y in caps, months as M in caps, weeks as W in caps, days as D in caps, while the time units are hour in small h, minutes small m, seconds small s, milliseconds small ms. The usual ones like now is also supported here, which returns the current datetime in UTC format. NumPy datetime actually does not store any time zone information like Python. It handles offsets by converting to UTC. You can format the datetime precision using M for months, D for up to days, H for up to hours. You can therefore convert a datetime type string of array to datetime 64 in NumPy. Create a host of values using numpy.arange, specifying the start and the end date range, and dtype as y, months, days. For datetime manipulation like adding or subtracting time or dates, time delta 64 is used, just like Python. There are 4 types of time delta: W, D, M, and Y. D and W, that is days and weeks, are compatible with each other. So if you have something like np.time delta 64 1, W modulus np.time delta 1, D, it will return numpy.time delta 64 with days format. Y and M, that is year and months, are also compatible, but W and D are not compatible with Y and M. A time delta day unit is equivalent to 24 hours, but there is no way to convert a month unit into days because different months have different number of days. You can cast a time delta into another time delta type according to the above mentioned rules. I'm not going much into the details here. The rules are similar to Python datetime and time delta. But what sets NumPy datetime apart is the dedicated support for business day functions and business day calendar object for specific operations on business days specified as past day here. But the default for the implementation is based on a weak mask containing 7 Boolean flags to indicate valid days. Custom weak masks are also possible if you like to specify other set of valid days, since not everywhere Saturday and Sunday are off days, which are by default set here. The past day functions can additionally check a list of holiday dates, specific days that are not valid days. And there is this function busday offset that allows you to apply offset specified in business days to datetime with a unit of D. It makes it very easy to find out the exact dates if, say, Amazon asks you to expect that refund by the next 5 to 7 business days on a Wednesday, with a national holiday perched on Tuesday next week. So then there are functions like is_busday to find out if a certain day was a business day, and busday count to find out the number of working days between 2 date ranges. I'm not diving that deep into this one because since we mostly will be using Python and Pandas datetime to make the calculations. But I think again it's good to be aware that NumPy has a similar functionality too. Finally, we have reached to the end point of our discussion. I will finish it off with random sampling useful for machine learning. Suppose you have a data set you would like to split to training and test data. It is best to shuffle the data before doing that, and there are 2 ways to do it. Number 1 is by np.numpy. NumPy and np are used interchangeably here. Very late to say that anyways. np.random.permutation, where you pass on the array argument and you get a shuffled copy of the original array passed. The other one is np.random.shuffle that shuffles the original array in place. So it does not return any copy here and definitely is the memory efficient one. But yes, the original array gets modified. So you need to use your choice, use your discretion to choose between the two based on your data and how you want to preserve your data. Both of them shuffle and the first axis, that is row. So technically both behave in the same way. In machine learning, you often need to reproduce the results, and this exact reproducibility is challenging when you are randomly selecting the data. So to make things reproducible, a pseudo-random generator algorithm is used. So what you do here is you create a generator object using np.random.default_rng, that is random number generator, and you pass on the seed, which is an integer of your choice. You can use this generator object to create a NumPy array of your desired shape and size, and it will always produce an array of the same random value for the same shape and size. But here's what you need to remember. Whenever you want to create the reproducible reproducible result, like if you want to create two arrays with same values, create the generator objects with the same seed separately for each array, because otherwise if you use the same generator object twice, the values will differ. So you have to create the generator twice with the same seed. So here we are. Congratulations to you to come this far in the discussion. It was a very long video, so I appreciate your patience, and if you liked the episode, do share it with your friends and stay tuned for many more to come. Bye.